let's take a gander here. Our goal for this day is we're going to use something called the scatter plot in order to describe the relationship between two data sets. And data sets are things that are happening. For example, the screen size of a television and its cost. So that's what's happening in this table. So Nicholas plotted data points to represent the relationship between screen size and cost of television sets. Everything about the televisions is the same except for the screen size. So they're all smart televisions. They all have HDMI ports. They all have stereo surround sound, that kind of stuff. So all the ancillary things are the same. Even we would argue probably resolution is probably the same too. So that's just to say that these are all the same device, just different sizes. Okay, so what pattern do we see? And it's probably easiest as we look here to see some sort of a basic overall pattern. So a pattern that we see here is that the line goes up. And maybe that's just a simple way to describe it. But as we're reading, the line is going up. If we talked about that mathematically, we'd say it has a positive slope, or it looks like a positive slope. What can you say about the size of a TV as the screen size gets larger, and cost of a TV here? So writing that as a sentence, we can say something like this. As the screen size increases, the cost increases. Or if you said it more colloquially, it's just saying, as the TV gets bigger, the cost is more. How much do you think a 46-inch, notice that 46-inch is not here in the list, nor is it on this one here. So we had to make some sort of a, if this is 46, we have to make some sort of prediction about what the cost is for a 46-inch. And then the next question here is, well, what about a 60-inch, which is off-grid? 60-inch is going to be off-grid. And if I try to keep this to scale, 60-inch is going to be another 10, right? So 60-inch is somewhere over here. So what type of number do I expect here? So one prediction we could make is that 46 is between these two numbers, almost in the middle. So somewhere in the middle here is probably a good predictor as well. That's true. And if we look here at 46, and I would not put 46 here, just based on the trend. And I would not put 46 here because that's too high. So I'm looking in this region somewhere here. So my guess is it fits kind of nicely right there. So if I did interpret this, if you said 440, 430, 450 is probably reasonable as well. So for a 46-inch, we would say is approximately $440. And that's a reasonable interpolation. There's a great word for you. Next, what about this one? Good. Now this one's a little bit harder because we don't actually have the grid itself, and so we're taking not just estimates, but we're taking the estimate of estimates. So it does get a little bit more complicated. But clearly I would not put 60 right here. I probably wouldn't put 60 up there, although it could be. Based on, I don't know, the trajectory of the lines, right? I'm guessing somewhere here, based on the trajectory of those, which puts me somewhere here, which looks to me, 600 is probably there, so slightly higher than 600. So my guess is a 60-inch is going to be approximately 650, 630. Yeah, anything above 600 is going to be a reasonable dealio. So our first line of business, when we're talking about this topic of scatter plots and lines of fit, is we're going to understand something called association. So consider the following graphs. what can be said about the independent variable x? So this right here, as something happens to x, what is happening to the dependent variable y? So look at the very first one here. Notice that if I were to draw a line trying to describe these, a single line that describes everything, notice that as x increases, so does y. So just for shorthand, I wrote this. As x goes up, y goes up. And I'm going to write that in words using hours after sunrise and the current temperature. This is called a positive association. And we can write a description something like this. As hours after sunrise increases, temperature also increases. So that one is called a positive association. Well, clearly, if we do the other direction, we get a negative association. And the negative association can be summarized as I did below here. That says as x goes up, y goes down. As x increases, y decreases. So to put that in the context of this problem, as hours after sunset increases, then we see that the temperature decreases. And the last one here is just simply no association. When there is not a single thing that we can say, although some of you in a class, in fact, I might as well say, oh, look, it kind of looks like it's going downward-ish. However, notice that it jumps. As this goes up, here we have low, high, low, lower, but then low again, high again, low, so there's not really a pattern that the other ones clearly have. Notice with this one, I can sort of sketch a line that kind of describes it, right? This one here, I can sketch a single line that describes it. This one here, there's not really a line that works. So there is no real description. The description is there's no association. There's no relationship between the hours after sunset and the amount of rainfall. And of course, logically, we wouldn't think so either, because the sunset and rain aren't necessarily connected. There could be some sort of complex thing that we don't know about, but so far we don't know of a relationship between this. Or some other random thing, right? Hours after sunset and how many miles you walk your dog, right? There's no necessarily relationship between the sun and that. So, how would you describe in words what's happening with this table? Feel free to talk to your neighbor about it. Notice the two labels that are on the table. Go. So, in terms of association, we do see that we could describe it or simply label this as a negative association. But now let's be more specific in how we describe the scenario. So when we describe it, let's use the context of dollars and sales. And here's a good description. As cost in dollars increase, the sales decrease.
All right, so in part 3 here, we're going to understand correlation and trend lines. So as we saw with association, it's a type of generalization. If the association seems to be, so notice these are like B's, and they're all kind of flying. And if it seems to be that the association is linear, then we use the term correlation. A line that can be drawn among the data is called a trend line. And when I say among the data, I don't mean that it actually touches the data. Like technically it doesn't have to touch this point or this point or this point. It doesn't have to touch any specific point. Just to give an example of it, if you had data that did this here, you might have a line that goes among the data like this, but misses all of them, doesn't touch the single one, and yet it still would be a trend line because it's going among the data. So what we do here is our first step when we are looking for that trend line itself. If we're going to do this by hand, number one, we're going to draw a line that goes among the data. And this is a subjective because your line might be different than my line, might be different than your neighbor's. Then like we did last chapter, we're going to choose 2 points on that line, and then we're going to find the equation in slope-intercept form. So as I start to draw, best to have a ruler of some kind. And when we draw, notice here that if I drew this line right there, that doesn't seem to work so well because of, it just doesn't seem to describe the data. It looks a little bit too flat here. So I'm going to try another one. Clearly, something like this doesn't work either because it's not even among the data. So I need to find something that goes among the data with some below and some above. And it's just a coincidence that some of the points are touched. It doesn't ever have to happen that any point necessarily is touched. So your line might be a little bit different. Maybe you did based off this point here and kind of tried to fit it in between like so. But I'm going to use this line right here. For this guy over here, we can do the same thing, but this time we have a negative correlation. That is, the trend line has a negative slope. So when I graph this, notice my lines go like this, and some of the points are above, some are below, but the trend is that it's going in a negative direction. Okay, so what are my steps? I need to now choose any 2 points on this line. Now again, we're not choosing the points that are given to me necessarily. What we're choosing is 2 nice points on the line. So actually notice this one, 6 here, and 65, 66, 66, that's it. So I'm going to choose this point right here, which is 6 and 66. And I need to find another one. And if I can't find a nice point, wait, this actually looks pretty good, an 11 and a 72. 11 and 72. If I didn't have something that was nice like that, then I would have to estimate something. Just for an example here, at 9 here, this 9 right there looks like it gets to about, so that's 70, so it's slightly shy of 70, so what, 69.5, something like that. So that's where we just have to be somewhat subjective. We have to take a guess, kind of. But I did find 2 here that work out pretty well, 666 and 1172. So I'm going to use those here. So here are my 2 points. And now I'm going to subtract the y's. So 72 minus 66 divided by, and subtract the x's, 11 minus 6. And now we just simplify here. 6 over 5. Okay, next we're going to substitute into point slope form. We're just going to choose one of the points, and it doesn't matter which one. I'm going to choose this point right there. So I say y minus 66 is equal to 6/5 and x minus 6. A couple different ways to approach this one. I'm just going to take this method where I'm going to distribute the 6 this way and distribute the 5 this way, just so I can get rid of the fraction, although it's going to come back at the very, very end. Equals 6x minus 36. Now I'm going to add the 330 to both sides. 6x minus 294, and I should have a plus. And now I'm going to divide everything by 5 here. Now, in dividing everything by 5, I get some fractions that don't really, they seem awkward. Now, I can leave this in fraction form, 294 over 5. But let's interpret this, because each one of these has a nice interpretation. The 6/5 means something, and the positive 294 over 5 means something. Okay, now let's interpret. First off, my b in my slope-intercept form there, the 294 b is equal to 294 divided by 5. And what does that equal? Is 58.5. 0.8 what? Degrees Fahrenheit when? That means when sunrise happened. At sunrise. At sunrise. Okay. Now, of course, this should meld with your data. Not perfect, but close. Notice right here. This is 60 degrees. This is 58, so it's slightly higher than 58. So it turns out that this piece of data actually fits on my line, but it doesn't have to. This point right here does not have to match with what you just came up with. Okay, and now what does the slope mean? Well, 6 over 5 is going to be 1.2. 1.2 what? 1.2 degrees Fahrenheit increase every hour, because it's over 1. Every hour. Every hour. So as we see here, it goes up a little bit more than 1 degree every hour. So here we go, a little bit more than 1 degree. Here we go, a little bit more than 1 degree, 1 degree, all the way over to here. So after 10 hours, we expect a 10 degree, more than 10 degrees going up. All right. I'm going to do the same thing over here, but I'll let you work through that, and I will turn the page. Okay. Now, just to get you started on this one, we can draw a nice line. Again, use a straight edge for that. And I'm going to draw something like this. Notice my point does not have to actually, my line doesn't have to touch any point at all. It doesn't have to touch any point. Excuse me for a sec. Hello. So we've got some points above, some below, so we've got a little trend line. So now we're going to choose 2 points. I'm going to select, turns out this 2,8 works out pretty well. So 2,8 is one of my pieces of data that I'm going to use. Just happens to coincide. Like we said, most of the time it's not necessarily going to fit. Now I'm just going to randomly choose this one. 6 is there, and what does that look like? 4.25? 6 and 4.25. Like so. All right, so now we're going to start making, do slope, and then use y minus y1 equals m times x minus x1, and see what we get. And here's what I get. Now my slope, to get this, what does this mean? This means that the cost for every single time we add a dollar, the cost in dollar goes up for this product. That means the number of sales goes down by this many million. So 937,000 less in sales for every time you add $1. So when something costs $6, you sell significantly less than if you sold it, if you had something for $2 there. Okay, I do want to point out, because of this break in the line right there, in the axis, notice that this is actually not accurate right there. Technically, it's going to break right there and go a little bit higher, which is why my number right here seems so odd. 9.875. What do you mean? How did I get that? Because year 0, this looks like 8 point something. That's because there's a break right here, and I'm not accounting for over here. So technically, it should be extended to be over there. So that's why my number looks incorrect, and technically, I shouldn't have that line component there. So this is what I end up with for my model. Okay, now the last thing we're going to look at is using trend lines. And the key on this one, of course, is once we have it, we plot the points, draw our line, and come up with our model, find the trend line that I did. We're going to use that model to predict and see if the 2019 data makes sense. So first thing I'm going to do is plot the data. And now I'm going to draw some sort of a line that passes among everything here. So let's see, looks like this might work fairly well, like so. I've got some below, some above, something like that. Turns out, coincidentally, this data point looks like I'll use, and maybe even this data point right here. So it's only a coincidence that I'm actually going to use the data given here, because that generally doesn't have to happen. So let me go ahead and use those 2 points, which is my first, the 0th point here in the year 1999, and let's use this one as well. So here's what I got. And remember to interpret this. This means in the year 1999 that $5.08 is the cost. This here says about 25 cents, 24.3 cents per year increase. So now to make a prediction for the year 2019, that means X has to be 20 because that's 20 years after 1990. So all we do is substitute in 0.243 times 20 plus 5.08, plug that into our handy-dandy calculator, and I got this. In 2019, it's going to cost $9.95. Now, if I look at some data, in fact, our personal experience is going to be a little bit, this is too low. My guess is $12 to $13 is what most of us experienced. So in the end here, this model might not actually be very good, although I don't have aggregate data for the entire country. And that is how we use trend lines. Enjoy.